If you know absolutely anything about science, anything at all, you know that it's impossible to go faster than the speed of light. And that's pretty much true, although a little caution is required. There are a few situations where it's actually possible to break that ultimate speed limit, although if you think that this will lead to something like this,
engage,
you'll be disappointed. Sorry about that. I made an entire video on the special cases, which you might want to look up. In this video, I want to tell you about one of those special cases, but it'll be backwards. Rather than having an object going near the speed of light and then speeding up, instead, I'm going to talk about a situation where an object is traveling at near the speed of light, and then we slow light down. That's a bit of a cheat, of course, but it's still pretty interesting, so let's talk about it. When we talk about the speed of light, we really mean the speed of light in a vacuum. When light encounters a transparent medium like glass, plastic, water, or even air, it slows down. You may have heard of this if you ever took an introductory physics class. The phenomenon is called the index of refraction, and we know that in glass and plastic, light travels at about 2/3 the speed that light travels in a vacuum. In water, it's about 3/4, and in air, the speed is only a tiny bit slowed down. So that's the trick. Suppose you had a vacuum with a light beam in it with an electrically charged particle like an electron or a proton traveling alongside it at very nearly the speed of light, say 99.99% that speed or something. The two of them would stay together pretty much, although the photon would slowly pull ahead. Now, suppose that we shoot the two of them into a huge tank of water. If we did that, the electron would continue to travel at 99.99% the speed of light in a vacuum, while the light beam would instantly slow down to 75% its normal speed. In this situation, the electron would be traveling faster than light. Boom! Mind blown. So having a particle travel faster than light is already a kind of cool thing, but it actually gets even better. The first person to notice that the liquid surrounding a radioactive substance glowed blue was Marie Curie, because, well, you know, Marie Curie. She was totally the bomb. But the person who typically gets the credit for the first observation of the phenomenon is a Russian student by the name of Pavel Cerenkov. He first saw it back in 1934. Now, before I tell you about the physics, I'd like to talk a little bit about how to spell his name. Because he was Russian, the proper way is to use the Cyrillic symbols. On the other hand, on the English-speaking internet, you typically see it spelled Cerenkov with the CH, since that's the sound that starts his name. On the third hand, you'll almost never see it spelled that way in a physics book. In a physics book, the name starts with just a C, not a CH. And occasionally, you'll see the name written with a C with this little accent symbol on top of it. So, I don't know what a real linguist would tell you is the right way to transliterate the Cyrillic. But I always say that, well, physics is everything. From that, I conclude that the physics way is the right way. And from that, I can authoritatively tell you that you spell it with a C and no H or accents. Or not. I'm a physicist, not a linguist. What do I know? So let's move on. When Cerenkov saw the blue light emanating from water surrounding a radioactive sample, he told his advisor, Sergei Vavilov. Vavilov shared the observation with two of his colleagues, Igor Tamm and Ilya Frank, and Tamm and Frank figured out what was going on. It turns out that when an electrically charged particle moves through a dielectric medium at a speed faster than light moves through that material, light is emitted, and that light is called Cherenkov light. Now, the exact detailed mechanism whereby light is emitted is quite complicated. Maybe I'll describe it in a future video. But basically, it's created because the electric field of the charged particle disrupts the electrons of distant atoms, and those disruptions cause even more disruptions to other atoms. When you add up everything, Cherenkov light is emitted, but only if the charged particle is traveling faster than light. If light is emitted at a point represented by this X here, it radiates from that point in a sphere. You can see how it works in this animation. The sphere grows at the speed of light. But the particle, which is represented by this red dot, is traveling faster than the speed of light. You can see that the dot moves away from the X faster than the sphere grows. Now suppose light is emitted when the particle is set at a different location. That light will also leave the point in a sphere, and the sphere will also grow. This process can appear again and again and again with a series of spheres. The edges of the spheres line up, which you can see here. And of course, light isn't emitted just at these locations where the X's are marked. The light is emitted everywhere along the path of the charged particle, and the result is a cone of light growing around the path taken by the charged particle and traveling forward. So those are the basics. A charged particle traveling faster than light in an appropriate material results in the particle and material combining to give off light. That light tends to be from the purple and blue side of the spectrum. I'll show you an example of that in a minute. But scientists can use more information than the simple observation of blue light. The shape of the cone tells you how fast the particle is going. If it's going near the speed of light, then the cone is very fat. But if the particle is going much faster than light in the medium, then the cone is very skinny. Another thing scientists can exploit is the fact that some particles are created in the transparent medium moving just faster than light, and then, because of interactions with the medium, they slow down below the speed of light. That means the particle will emit Cerenkov light for a little while and then stop doing so. And that means that the light will not be a cone forever. Instead, you'll see a gap between the two wavefronts. Now, what I've shown you here is in 2 dimensions, but of course, it's a 3-dimensional thing. The light comes out as a ring. This particular feature is very useful in huge Cerenkov detectors. For instance, the Super Kamiokande experiment in Japan is a ginormous tank holding 50,000 tons of water. It's a cylinder about 40 meters both in diameter and height. That's about 130 feet for Americans. In the Super Kamiokande detector, or Super K as it's often called, neutrinos enter and interact with the water. The neutrinos convert into electrons or muons, which are charged particles that can emit Cerenkov light. That's basically how it works. Some of the neutrinos that interact in the water are low enough energy that electrons or muons don't travel very far. Therefore, the Cerenkov light makes rings inside the detector. Using the size of the rings and the time the light arrives at detectors throughout the apparatus, scientists can figure out the energy and trajectory of the parent neutrino. Really a very cool technique. Cerenkov light is used for many purposes in particle physics experiments, but it's probably mostly used in these big water neutrino detectors. If you're interested in other applications, you can, of course, Google it. Before I close, I want to share a very awesome video. In this video, a nuclear reactor is surrounded by water, and the reactor is turned off. As the technicians turn the reactor on, it begins to emit countless charged particles into the surrounding water. And as it does, you can see the Cerenkov light begin to be emitted. It's one of my favorite videos. Okay, so that was a longish video, but Cerenkov light is a fascinating phenomenon. If you like what you saw, please like the video, share it with your friends, and subscribe to the channel. I want this channel to have more subscribers than any of America's other national labs. I'm confident that we'll do that because unlike those, well, multi-purpose laboratories, our focus is simply jaw-dropping physics, and, as I'm sure you'll agree, physics is everything.